When we speak of the cloud, we often look toward the sky. We imagine our data drifting through the atmosphere handled by a network of satellites orbiting the Earth. But the reality is much more grounded and significantly deeper. Roughly 99% of all international data is not transmitted through the air, but through a hidden network of cables resting on the ocean floor. These thousands of miles of glass and steel form the actual nervous system of our modern world, connecting continents with pulses of light that travel through the dark, high-pressure silence of the abyss. Today, there are approximately 800,000 miles of fiber-optic cables lining the seafloor. To put that into perspective, it is enough to circle the Earth more than 30 times. These cables are surprisingly thin. In the deep ocean, where the environment is relatively stable, a cable is often no thicker than a garden hose. At its core are strands of glass as thin as a human hair. Despite their delicate appearance, these strands carry the weight of the global economy, from trillion-dollar high-frequency trades to the very video you are watching right now. This physical connection isn't a new concept. The history of the underwater internet began in the 1850s, not with fiber optics, but with copper telegraph wires. In 1858, the first transatlantic telegraph cable was completed, connecting Ireland and Newfoundland. It was a monumental feat of engineering for the time, though it was plagued by technical failures. It took 16 hours to send just 98 words. While the technology was primitive, it established a fundamental truth that remains today. The fastest way to move information over long distances is to lay a physical line across the Earth. The physics of modern cables relies on a principle called total internal reflection. Inside each glass strand, data is encoded into pulses of light produced by lasers. As the light travels, it hits the boundary between the glass core and its cladding at a shallow angle, reflecting back inward rather than escaping. This allows the signal to zigzag through the fiber over vast distances with minimal loss. Because light travels so quickly through the glass, the latency, the time it takes for a signal to cross the Atlantic, is reduced to mere milliseconds, a speed satellites cannot yet match. While the glass fibers carry the data, they require significant protection to survive the journey. A standard deep-sea cable is composed of multiple layers. Around the fibers lies a buffer of petroleum jelly, followed by a copper tube that carries electricity to power the system. Outside of that, layers of steel wire provide tensile strength, wrapped in a final skin of high-density polyethylene. Near the coastline, where the risks from ship anchors and fishing nets are higher, cables are further armored with thick layers of steel wire, making them resemble heavy industrial pipes rather than data lines. Physics dictates that even the purest glass will eventually absorb and scatter light. Every 40 to 60 miles, the signal begins to dim. To fix this, engineers install repeaters. These are large, pressurized cylinders integrated into the cable line that act as sophisticated signal boosters. Inside, erbium-doped fiber amplifiers use the electricity from the cable's copper layer to re-energize the light pulses. These repeaters must be incredibly reliable. They are designed to operate without maintenance for 25 years at depths where the water pressure is equivalent to an elephant standing on your thumb. Laying these cables is a slow and deliberate process. Specialized ships use a plow to carve a trench in the seabed where the cable is buried to protect it from interference. In the deep ocean, the cable is simply laid onto the abyssal plain. The environment here is harsh, near freezing temperatures and immense pressure, but it is also remarkably quiet. Most damage to the cables isn't caused by nature, but by human activity, such as bottom trawling or dragging anchors. When a break occurs, specialized repair ships must go to the exact coordinates, retrieve the cable, and splice it back together. Once a cable reaches the shore, it enters a landing station. These are often nondescript buildings located near coastal towns. Inside, the undersea cable is connected to the terrestrial fiber network. This is where the ocean meets the land. These stations act as the gateway for entire countries. If you are in New York and access a server in London, your request travels through your local fiber, hits a landing station on the coast, dives into the Atlantic, passes through dozens of repeaters, and emerges on the other side, all in less time than it takes to blink. As our demand for data grows, specifically with the rise of artificial intelligence, we face a new problem: heat. Terrestrial data centers consume enormous amounts of energy, not just to process data, but to keep the servers cool. Roughly 40% of a data center's energy goes into cooling fans and air conditioning systems. This has led engineers to look back toward the ocean, not just as a path for cables, but as a potential home for the servers themselves. The deep sea is a natural infinite heat sink that could solve the efficiency crisis of the AI age. Microsoft's Project Natick demonstrated the viability of this idea. They submerged a self-contained data center off the coast of the Orkney Islands in Scotland. The cold seawater naturally cooled the servers through a heat exchanger, eliminating the need for energy-intensive cooling infrastructure. Surprisingly, the servers in the underwater pod were 8 times more reliable than those on land. The stable temperature and the nitrogen-filled atmosphere, which prevents corrosion, created an ideal environment. This suggests a future where our data centers are co-located with the cables that connect them, hidden beneath the waves. The evolution of the internet's infrastructure is moving toward a more integrated relationship with the ocean. As we build larger AI models that require massive compute power, the proximity to both cooling and high-speed subsea cables becomes vital. We are moving toward a world where the cloud is more accurately described as a submerged machine. This hidden world of light and glass, buried in the sand and cooled by the currents, is the invisible foundation of our digital civilization. It remains out of sight, yet it's the only reason the modern world functions as it does.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.